I'm here today with Matthew Day, my colleague. I'll leave his contact information at the end, but he'll answer some questions during the presentation, and then he'll interrupt me if there are something that he wants me to answer, and we can sum up at the end. But I was invited. Thank you, Martin, too, for inviting me to this forum. I've heard of it. It's not new to me. I was introduced or invited last week, kind of last minute to step in with someone. But when I started thinking about it, we actually have quite a bit of material that we have tested out towards NDE 4.0 and digitalization. So I'm excited to show you some of the concept and ideas that we've tested out. But before that, I'm going to introduce you to our technology so you understand where we're coming from and why that is a perfect setup for digitalization. And then I'm going to move over to the NDE 4.0, which covers synthetic focusing, which is just to show you how we can use the tremendous amount of data we have. And then I'm going to talk about a local positioning system that we have tested, and 3D mapping and projection of the NDT data. And this kind of combines into like remote NDT and digital twin, and how we could, in theory, move on from here. And then lastly, I got 3 examples of automation and robotics that I've done. So when I'm explaining the technology I like to just take a step back and go back to the ultrasound transducer basics. I think most of you are familiar with the ultrasound, some more than others. But anyways, here's a picture of the standard components that you need for an ultrasound transducer. You have the most important material here, which is the piezoelectric material, which has the acoustic property that we want. And then you have 2 conductive layers here, one on the bottom here, which in this case is connected to ground, and the top one, which is connected to transmit and can be switched over to receive. So what happens if that when you put a square pulse, let's say 100-volt pulse into transmit, then you create a potential between this ground and this transmit electrode. And then the piezoelectric material starts to vibrate. And the vibration creates an ultrasound wave that goes through the delay line into your material, and it hits either a back wall or a floor or something, and then it comes back. And then when the sound comes back, you create another vibration, which causes inside the piezoelectric material, which causes a tiny little electric charge, which goes over to the receive electronics and is amplified, and it creates your pulse echo. And that's what you're seeing here on the left side. So you have the standard UT ultrasound testing single element. We're showing two examples here of the wave. This is just figurative because it's a one wave single element, but in one case it hits the back wall and goes back. In other case it hits the crack and goes back. And then from this pulse echo single element, you get what we call an A scan. So you see the penetration echo here in the beginning, and you see the back wall echo here at the end. And operators use the amplitude of this pulse and then the time of this pulse to kind of assess the inspection. So for example, if you hit the back wall here, you see that the A scan is very clear and nice, and it comes at a certain time here, which is can be transferred into depth. For example, a corrosion or a thickness measurement. And if you hit a crack here, this pulse will appear earlier, so indicating that you get a reflection earlier, which would be a crack or a corrosion or something. And the size of the A scan also says something about how the nature of that the sound was the sound hit on the way to the back wall. So this takes a lot of hours to train and be an expert on. And then a couple of decades ago, they started putting these elements next to each other and get what you call a 1D array. They call it a phased array because you can phase the sound to focus in areas. But for simplicity, let's focus on the 1D array. And that's pretty much many A scans aligned together. This transducer shows 16 elements, but this B scan is actually from 128 elements. So if you look to take the A scan, you kind of flip it and then put it vertically down here, and you say if the signal is low, then it's black. If it's high, then it's white, and everything in between. So you can imagine this A scan. The beginning here is a little bit gray, and then dark, 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 and then it gets white here where the amplitude goes up. So this creates this B scan. You can see the penetration echo, the back wall echo, and then some cracks or whatever in the middle here. So it's kind of like dicing through your material and seeing it in from the side. Then the matrix arrays, that's a 2D array. So instead of just elements in X direction, we have an X and Y. Then we get an A scan per this element, and all of a sudden we have a volume instead of a cross section, and that makes the interpretation of the result a lot easier. And it shows you what we call then a C scan, which is a horizontal or cross section the other way, or you're actually capturing an area of the thickness and then presenting it, and you can see the 3D volume here as well. But this is better just to demonstrate. So what I'm going to demo now is the Dolphitech 2 system. You have a transducer module, which you see here in the front, and then you have a tablet, which you will see here now. And behind that tablet is actually a black box, which has the communication to the tablet and battery and power and so on. By the way, Martin, can you see my cursor when I move it around?
Hang on a sec, just move it. Yes, we can perfectly. Yeah, it's moving along.
So right now I'm showing you the transducer module. I have here a piece of carbon fiber. This is from an Airbus A350, and this has been impacted, and you cannot see the damage on the outside, but it has indeed cracked the inside. So if I spray this with water, put on air and I start scanning, you can immediately see this C scan here. So if I stop scanning here, just to kind of explain the picture. This is a C scan time of flight, which means it shows you the color, or it shows you the depth of the flaws. So every element has an A scan, and I got 128 A scan in each direction here, which is a 16,384, and each element, you can see where I click around here, has this A scan. And in this picture, the C scan, then the time or the depth, if you will, is translated into a color on this color scale. So I have 4.9 millimeter here. I can go to green, which is 4.06. The orange is 1.92, and so on. So a very detailed picture of the damage. I can also choose where in this C scan I want to see my two B scan vertical and B scan horizontal. So this is where the time information is used, but we also have C scan amplitude. And if I scan around here, you can see more a picture that looks more like like an X-ray picture or whatever. And then to kind of overwhelm you, I can show you all of this at the same time. I can hear some audio from Julio here, I think. So yeah, here you go. You got a live streaming C-scan time of flight, C-scan amplitude, and 3D here down at the corner. So that was a quick introduction to the technology. Now, if we go back to the demo, I got a few examples. I'll run through those quickly, but here's an inspection done out of a Dreamliner Boeing 787, where the trolley drove into the fuselage and created damage. So you can see the impact damage here, the time of flight. This is actually a mapped picture, so the picture is a lot more than the transducer aperture. So you can see the impact damage here, and you can also see the stringer has disbonded here a little bit.
Sorry, someone's talking in the background. Can you mute your microphone?
I just muted. It is Julio. I muted him.
Okay, thanks. Cheers.
Moving on to the next one. This is a wind blade with flat bottom holes, just to indicate that we can see through our glass fiber. So this is about 1.5 inch of glass fiber. This is aluminum, a corroded piece of aluminum, actually. Again, down here you can see the blue thickness and then the corroded area here in yellow. Same with the amplitude C-scan. And then just lastly, some bonded material, different materials bonded on carbon fiber, aluminum, plastic, steel, and so on. So that was just to give you an indication of what the transducer is used for, the technology. But one important thing that I wanted to mention, that I mentioned 128 times 128 A scans. So we get 16,384 measurement points just from one picture. And we can stream up to 20 frames per second. If you map together a large area, you can imagine the resolution of the data we have. And this is important because you can use the data for so much. For example, here's an example of statistical representation of the data for porosity inspection of, let's say it's for thickness. So in this case, I'm showing all the different amplitudes I have within this area here. So the green square probably represents 12,000 data points, right? So in this case, it's amplitude. And if I was measuring through a piece of aluminum with no damage, they would all be distributed, for example, around 80%. But this distribution could tell you something about the porosity of the material. Or if it was thickness, you could see something about corrosion, right? You can have pitting corrosion, you can have standard corrosion, you can have like the one area is thicker than the other, and that amount of data that we saw in the presentation here we had earlier, that was very, very well presented data. They were probably measured per 1 inch or whatever. This here we're talking about 4 measurements per millimeter in each direction. So quite a lot of data. But now over to the important part of the presentation that has to do with digitalization and NDE 4.0. My point with the intro here is that the start situation with all the data that we can have is very fit for use of AI and digitalization and NDE 4.0. So I'm going to first tell you something that's not related to the other, but it's synthetic focusing, and then a little bit about local positioning system and 3D mapping, which I said will bring us into remote entity and digital twin, and then some examples of automation and robotics. So with all this data, we can focus our results. So let's say you've done your scan, we have 20 scans per complete scans per second, so 16,384 times 20 per second. But if you take one of those sets, you have 16,384 A scans. And you can choose different areas under your transducer where you would like to focus. I'm not going to go in detail of how we implement this, but the point is, I can choose, for example, this blue line here, this focus point right here. I can delay all of my 16,384 A scans so that they arrive at this point at the same time. Likewise, I can, on this red triangle, I can delay all the A scans to arrive at this point, and likewise at this point for the green. And then you get some synthetic aperture focusing technique. So you get a sum of 16,000 elements or measurements on that one point. And that's the result you can see here. You got an unfocused C-scan. This, by the way, is a Rexolite sample that we have with different depths. You go from the unfocused to the focused, and you can see a 3D presentation down here. So incredibly detailed view of cracks and stuff is possible. So this one's not necessarily related to my next ones, but this is several years ago that we created a prototype of a local positioning system where we used an infrared system to point towards this orange piece of plastic here with LEDs, so it can detect your position in X, Y, Z, and ABC, so both 3D and rotation. The demo we did was in 2D, but it can be done in 3D where you kind of paint your results directly on your sample. So here we see a colleague of mine kind of painting over a composite plate with impact damage, and the infrared camera is filming the orange piece with the LEDs, and then it is pairing this positioning data with a timestamp of the NDT results. So we can paint the result on exact location of where the A-scan was taken. This is pretty cool and magical. You're kind of painting on something that's hidden under the surface. And then another company, I think it was a university together with in Holland, in Netherlands, they took our, and if you want to know who exactly it was, I should have referred it here, but I think it's part of the video. But they used VR glasses, and then they mapped our data on top of the piece that they were inspecting. So showing here you can see they are also doing the mapping. They're not sliding, but they're doing tile by tile. So it's 250 or 25 millimeters apart. You can see he's wearing VR glasses, and he's mapping one tile at a time. So he starts scanning and stops scanning. That's how you control when you want to collect the data. So here's mapping a little bit of a larger area. And this last piece of the video, you can see that the NDT result is kind of hovering over the actual sample. Yeah, here you can see now. So here you can see two areas with damage that are kind of showing up in 3D there. And you can, of course, control the intensity of transparency so that you can easily see both your part and your NDT result at the same time. Then, before I have a sum up slide of this, then this is quite a few years ago, we had two master's theses that did a thing on remote NDT, and remote NDT can be everything from a phone call to Zoom or Skype or whatever, but we kind of had some special functionalities that we wanted, and this is via a safe link from expert to operator. So you can see here where it's connecting two people here, one expert and one operator. My colleague Matthew here being the expert. I am me as an operator on the other side of the world. Matthew, the expert, sits with his computer. For some reason, he's staring into the back of the computer here, but nevertheless. So you can then you have an IP address as an operator, and you can send it to try to send it to an expert that you want to connect, and then you get this graphical interface up here. Now these are fake images, but it did actually work. And you have a two-way audio and video. You have a chat function. This is all fine. But then you have a remote control of the Dolphy account. So Matthew here can take control over my camera, not physically moving it, but control the settings and the setup, configure it correctly. And then we have an overview camera that is kind of further away that inspects the area that you're inspecting. And then you have a close-up camera, which is on your shoulder or your helmet or whatever that shows exactly what you're doing. So you can see the pressure, the amount of water you have on the inspection, and so on. And this worked really quite well. We used Amazon Web Servers for this. We did the demos in Norway, but we used the server or the data center we used was in the States. This is like 6-7 years ago, and the latency was fine. It was absolutely fine. We did another version of this with the phone, trying to exclude even the tablet, and we connected. Then this was another. This was a bachelor thesis actually, where they put our software on a microcomputer and which was run with a power bank, and you could even then use your phone to control the camera. So he's connecting the correct IP address, and you can tell by the phone that this is an old old video. And then so now he's setting up some gating, and then he starting to scan. And again, this is with a few years ago, so this is with the Dolphitech 1. And he starts scanning this plexi rolls that or Rexolite rolls that I just also demoed to you. So this is a microcomputer, and it's using Wi-Fi to communicate with the phone. So if you add all this together that I just showed you, you can imagine experts around the world, operators that doesn't necessarily need to be NDT experts. You get a vehicle or you get some sort of NDT part that you want to inspect. It could be an aircraft, it could be a windmill, it could be a car, but in this case, it's a plane. You can see he scans the plane with a QR code, and then all this history from this aircraft is loaded up. So this can be everything from projected NDT results to the actual aircraft, or it could be tables and reports. Let's say you can get a table of when the last maintenance was, a table of where it's flown, who owned it, displaying ultrasound, eddy current, all kinds of results or separate results. And if you start thinking all this data, if you can collect all the data and connect AI, then you could predict even accidents, predict maybe maintenance to save money. It just kind of explodes, right? But be able to do this, you really need, yes, it's boring, but you need some standards. Dolphitech cannot decide one way of doing this and then someone else does something else. I think people need to come together to agree on everything from file formats to rules and regulations, right? But I happen to study AI a little bit on the side now, and it has a ability to learn extremely amounts of things to do. Not just words, but it could probably take data and look at different data, not necessarily the NDT pictures, but the NDT results and connect it together. So I'm sure all of you can just imagine how this could be used, but just the digital twin part used manually would be tremendously helpful, I think, for someone that has a huge fleet of cars or huge fleets of windmills or planes. Then leaving that part of the presentation of AI and remote NDT digital twin, and just showing you 3 examples of robotic implementations that we've done. One is we just did recently on an exhibition in the States is a 2D mapping of a robot together with the SDK, just controlling the software and the robot at the same time. Automatic COPV, which is composite pressure vessel, and then robotics TTU. TTU, MX stands for our matrix. TTU is through transmission ultrasound, which means from one to another instead of pulse echo. But let me just play the video. So first of all, this is so a script is running the robot, telling it to move 25 millimeters in a certain pattern, and then it tells the software to start and stop scan. And so it's mapping together a larger area. So this is very easy to implement. We have a software development kit that can be used for this. So it's nothing that we offer off the shelf, but it's definitely possible. Then the next we have a concept project kind of a composite pressure vessel. This is a market that is exploding. Hydrogen tanks and pressure tanks that needs to people are afraid of they exploding and stuff like that. So we want to be able to inspect them. So the concept was a robotic cell, which can be inspect everything from a smaller pressure vessel like this with one robot, or it could be extended to have several robots, either a moving robot or several robots that cover an area for larger COPVs. And yes, this was just a concept, but we did actually test this. And here is the example. It's a little bit blurry video because it's a commercial video, but behind the blur, you can see a robot moving onto a COPV, and the COPV is rotating. So of course you have control of the rotation and the movement of the robot, so you can map together a larger area. And you see a little cup here with water. So we had water pressure into the cup to create coupling. So, and this is all controlled from one computer script. So that was a pretty cool project, but not implemented somewhere in full scale yet. Now the last one is something we've done for exhibitions, but it's also very easy to do. You have a two-armed robot here. You could have two different robots, but they follow each other. So the point with T2 is to send sound from one transducer to the other, and there's many benefits for that from that I'm not going to go through now, but it's quite easily implemented. And this is something we had in the exhibition a few years ago, where the robot arms pretty much follow each other. So this is without, well, it actually did work, but we didn't have the the water system up and running, because that would be messy on an exhibition. So I hope that was helpful. I hope it was relevant. It was kind of two sections here, one with digitalization and NDE 4.0, but also an industrial part that shows you what we can do. And if you have any questions on like these robotics systems and stuff like that, that stuff we can do together with the customer, but it's not out of the box things that we have. Also including my colleagues, Matthew Day, information here, is the sales manager in Europe and UK. If you want more about the technology, more examples about the NDE stuff itself, or if you want to talk about NDE 4.0 or integrating this in automated inspection, just please reach out to either one of us, and we'll be happy to talk to you.
Yeah, thanks, Eskil. Thanks, Matthew. Such an astonishing mix of different components of NDE 4.0 all in one particular talk. I like the way you could paint the NDE information, the way you could include it in a digital twin, the way you could combine the visual and the other NDE data in the same package. Just a quick question about the use of the remote inspection. How often do you find that's used in practice? It's obviously very good in terms of giving a more reliable inspection if you can bring an expert in hand remotely to participate in the inspection.
Yeah, We've seen a lot of interest for it, but we haven't seen full scale of it. First of all, for example, airlines, they're a little bit concerned about having their data go via the cloud. But we do a lot of training remotely, but we don't use this specific software for that because this was just a master's thesis. But we do a tremendous amount of remote training, but remote inspection is not something that we see a full scale of. But the limited access to experts is an issue.
It is, yeah, and it's interesting in other domains, like in the subsea side, for example. For a long time, people have been producing the data subsea by divers, but then the data is being viewed and analysed and controlled topside in a particular plant. So the example there, where you can actually be in a different part of the world and you're able to actually control the inspection.
Yeah.
Yeah, there's a few more questions in the chat. I see you've answered a number of them. One is about the adaptability to surface contours. I guess that's the question of the probes you're using.
Yeah, and we have most of our transducers have something called Aqualine, which is relatively soft, and then we also have Rexolite, which is hard. But you can also get them without the delay line, and then put your own delay line on there. For example, something called clear ballistic gel we've used in several cases with success. And then we also have 3D printing capability of complete custom delay lines as well.
The sort of components you're looking at, is it mainly aerospace or quite a lot of work within the sort of oil and gas sector?
We are for sure mostly in aerospace, space, and defense. We actually, I would almost say all of the private space companies own our technology. And that's because we are very good at composites, but it also works well for corrosion. Corrosion and some types of weld or crack detection. But corrosion is a very good application for us because you get so much data. You don't have to use all the data, but you can use statistics like I showed you on corrosion.
Yes,
And
I mean,
of course, it's compatible with scanners, large scanners like pipe scanners and stuff like that. We have XY encoders, so you can plug it in and it works seamlessly.
Yes, corrosion is an interesting one because you're looking through thickness for indication of corrosion pits, and I guess in composites, one of the key elements you're looking for is delaminations, which is again a similar sort of C-scan through thickness. Another thing I found very interesting, because the technology you have sort of spans all the different areas of NDE 4.0, from the data acquisition, the data presentation and format, through to the use of the VR glasses and superimposition of the data. Is the use of I can see that using VR glasses could really speed up the inspection if the inspector is actually able to see in real time, straight in front of them, the data on the component. Is that something that you're using yet in practice, or?
No, this is only on concept, but we've proven that we can do it. It's possible. So we're looking for a pilot, or for all of these things, a pilot customer that would kind of invest a little bit, would kind of start a project like that. But it would take quite a bit to develop it, or not. It's not difficult, but resources. So we want to make sure that we get our money's worth before we put too much time into it. These are things that we like to play around. I'm the chief research officer, so we like to try different things and then disprove it, and then we show it to customers, and then if they like it, we can definitely do a project together.
Yes, no, I can see that, and I can see maybe it needs a more sophisticated inspection. And certainly one of the things you describe in the aerospace thing, I can see if you're looking at a wing or a fuselage where the large area that you need to cover in the inspections, I could see it could speed up things dramatically. A couple more questions in the chat. Is there any thickness limitations in application? Can it detect cracks on the ID of a vessel or pipe?
Yes, as far as thickness, that has to do with how we set up our software. We can do up to 60 millimeters of glass fiber. That's limited to speed of sound. So I think you're close to 10 or 12 or 100 to 120 millimeters of aluminum and steel. And yes, it can be used for crack detection, but we don't do any physical focusing. We do synthetic focusing, but with a physical focusing, it depends a little bit how the crack orientation is and the size of the crack, if we can detect it or not. But yes, it is used for crack detection.
Another interesting point you made was regarding the data format and data ownership and those particular issues. Those are, I think I agree with you that those are things in which there needs to be a common approach developed across industry. Are you involved in any interactions with people like the NDE 4.0 committees or?
Well, I was a part of the
groups.
No, not yet. I was a part of the FMC group where we discussed the format, but time I didn't have the resources to follow up, and it was a little bit difficult because everyone was 1D array or UT, and then we come with matrix array, so it was a little bit hard to get us fit inside that exact. I think we follow the standard, but I didn't use too much time to try to participate in it. So I can also mention that our file format is HDF5, so it's an open source file format, and one set of data, like one frame, can be up to 50 megabytes. So you can imagine 20 frames per second, and then a square meter of data. You have to be careful of what you save and how you save it.
Yes, no, and the way you're presenting all the data together in a single package, it shows a nice application of HDF5. We've had number of presentations in the forum on from the people involved in the HDF5 sort of developments.
Yeah,
so
okay.
that's great.